In this video, we're going to start in on trying to prove the fundamental theorem of arithmetic. There's going to be some intermediate results that we are going to prove along the way, and this is sort of the first one on our path to the fundamental theorem of arithmetic. And this theorem tells us that whenever we have a number bigger than 1, it has a prime factor. So there's a prime that divides it. We need bigger than 1, of course. And the way in which we're going to go about it is for this particular theorem, we're going to do an iterative approach. So that is, we're going to outline an algorithm for finding it, a lot like the Euclidean algorithm was an algorithm for finding the greatest common divisor. And then in other proofs, what we're going to do is we're going to phrase it in terms of strong induction. And you could come back and revisit this one after the other ones to try to apply strong induction to this. So, suppose we have such an a that's bigger than 1. We want to find a prime that divides it. Well, if a is already prime, then we pick p equals a. Nailed it. Otherwise, a is not prime. And by our characterization of composite numbers, it means that a is a product of two numbers, some a prime and some other m. And our a prime is strictly between 1 and a. Can't be 1 because then we're just writing a as 1 times m, and that's not it's not part of our characterization from before. So a prime is strictly in between 1 and a. If a prime is prime, then we're done because we pick a prime to be our p, then p divides a. We're good. Otherwise, a prime is composite. So we're seeing the cycle happen now. If a prime is composite, a prime is a double prime times m prime, where a double prime is in between 1 and a prime. But also, if we were to plug this equation back into this one, we would get a is a double prime m. So this tells us that a double prime divides a. So if a double prime is prime, then we're done. Otherwise, it's composite, and we repeat, and we get some a triple prime. That a triple prime still divides a by the same reasoning. And it's either prime or it's not, and we keep going. This process terminates. It terminates because each time we decrease from a by at least one step. In fact, we actually decrease down from a by at least a over 2 each time. So this process terminates. It actually terminates quite fast. It terminates, well, we won't go into complexity, but it terminates very fast. And eventually we'll arrive at a prime, and this is it. So this is the iterative approach to this problem. You could phrase the proof in sort of an inductive way, which again we will do for later theorems.